In panel data regression, we have 4 different assumptions which need to be in place. And why do we have to have these assumptions? It's because we have to know when we can trust our estimate of the beta, the slope, and when we can't. And these 4 assumptions, they resemble the assumptions for cross-sectional analysis. So let's get to it. The regression we are going to look at is the entity fixed effects regression, okay? The entity. So for each entity, you have a different intercept. Okay, so this is our example. So the first regression assumption is as follows. It's the expectation of the residual equals 0 no matter which value the x variable takes on in either of the time periods for that single entity. And it also includes the intercept. Okay, because the intercept varies across the entities. So for example, if I equals 1, we take the first entity, and t equals 2, we take the second time period. Then we would get the expectation of the residual for entity 1 and time period 2 given the values of entity x for entity 1 at time period 1 and the x value of entity 1, the same entity always, and time period 2, and so on until the last time period. In our case, we have 7 time periods, and we have to remember the intercept, and the intercept for the first entity, which is Alabama, the state of Alabama, and this should be 0. Okay, so the residual for the second year of data for Alabama, the residual should be 0. Okay, the expectation. the residual will, of course, vary, but the expected value should be 0. So you should not see a consistent positive or a consistent negative residual if you take several draws from the population. Okay? And this is actually quite important because it would provide unbiasedness. And why do we care about unbiasedness? It's because if we have the distribution of our slope, remember, the slope is our key interest, okay? And the distribution of the slope, or the sample slope, is centered around the true beta, the population beta. And of course, we could get a draw, or we could get a sample beta over here, but we know that it's centered on average on the true beta. And this is when we can actually use our probability theory to say something about is this a realistic value given the null hypothesis. Okay, and the second assumption is that for each I, for each entity, the draws from the x variables and the residuals are independently and identically distributed draws from a joint distribution. So this means that if we take some simple random sampling, so we don't just take a subgroup of the population and sample from this, but we sample randomly from the whole population, then we would get a simple random sample in which the draws are independent of each other and they are identically distributed. So, and this is important to actually get a good estimate of the causal effect, the beta. And thirdly, we have to have that the pair of the x and the residual have non-zero finite fourth moments. It means that we are unlikely to see outliers. And there should be no perfect multicollinearity. So remember from the previous videos that if we make these dummy variables, we always include one less dummy variable than we have entities or time periods. Okay? If we include one dummy period per entity or per time period, then we would have perfect multicollinearity. We could represent one of the dummy variables by a linear combination of the other dummy variables. So, why do we care? We care firstly because if these assumptions hold, then our estimator, our beta, is unbiased. Our beta hat is unbiased. And I tell you that if the true beta is here and the distribution of beta hat is centered around the true value, then our estimator is unbiased, because on average we get something around the true value. Our estimator is also consistent. This means that if we get more data, then we get a better estimate of, this is beta hat distribution, then we get a much narrower, okay, this is not very well drawn, but you get the point. If you get more data, then you are more certain of where the true value actually is. Okay, the confidence interval is much narrower if you have more data. And if these assumptions hold, then if n is large, then this distribution is normally distributed. And why is that important? It's important because if it's normally distributed or has a t-distribution, then we can actually calculate the area in the tails. So this is the tail probability. So for example, you got a beta hat, which is here, and what is the probability of getting something more extreme than your beta hat, given this null hypothesis of beta being here? Then this would be the p-value, the two-sided p-value of your test. Okay. So this is why it's important that these assumptions hold, that we can actually trust our estimate, and we can perform a hypothesis test with our estimate of the beta.